So my talk is going to be slightly different than the last three, and I think the last three were very good. You know, Dr. Parker, Dr. Roberts, Bill Gardner, you know, they're looking at some very, very fundamental studies about what happens when things go slightly wrong at very, very low doses of radiation, or you've got micronutrient problems, etc., or this, and I really don't like this idea of brain pressure changes. That oops me out a little bit, I'll be honest. So, but when I was in graduate school down in Florida, I was doing numerical analysis, numerical simulations in physics. And we would play around with, you know, in a theoretical sense, atoms and photons colliding against each other. And the goal was to say how much quantum mechanics could we throw at the problem and get accuracy, but at the same time we wanted to simulate something more than just a hydrogen atom, right? So I was part of a group called Quantum Theory Project. And the idea was to say just how many particles, atoms, molecules, how big could we get these things and still have a reasonable simulation? Well, you know, at the time, a protein would be a huge, huge structure. Right? So we didn't look at proteins that much, and but it was all the same. It was the ultimate goal, right? And eventually, maybe one day, you might be able to simulate a cell, right? Well, during this last year of my PhD, my father got cancer, and at some point, that cancer metastasized to his hip. And so one day, he's walking around, and he's like, I got a little bit of pain in my hip. You know, it hurts a bit. The next day, he can't walk. And I literally was, had to put him in a wheelchair to take him to the radiation oncology department because of the speed with which a metastasis to the hip can be painful. I mean, debilitatingly painful, right? And now I wasn't part of radiation oncology at the time. This was the hospital down the street from where I was doing my studies. A week later, after some radiation treatments, he's walking again like normal. And I'm looking at this thinking, this is the most fascinating thing, because it's like the ultimate extension of what I was doing in a quantum theory project, interaction of light with atoms, except there was no theory here. It was just throwing a bunch of radiation at his hip, and it was doing something which I perceived as miraculous. And sometimes personal events can change your life. So I finished my PhD, and then I went out and trained in radiation oncology as a physicist. And in the last decade or so, I've been involved in probably a couple of thousand of patient treatments, mostly cancer patients with radiation, right? So nonetheless, let me see if I can, even now, if I walk into a room and I see danger radiation, right, I feel scared. A little bit, because I think of the guy over there on the right. And with some reason. I mean, we have these little mishaps in Japan at various times, and it's absolutely certain that if I were, and I'm just going to throw a quick number here, if everyone in this room were to be exposed to 6 sieverts right now in a flash, what would happen to us? And probably for about an hour we'd be sitting there not even noticing, continuing on with our talks. And then we'd all suddenly feel like we had a bad flu, and we'd probably vomit and stuff. But by tomorrow, we'd be feeling better, whatever. A couple of weeks later, it would come back with a vengeance, and then about a month later, pretty well all of us we'd be dead. All right? And even with a lot of medical attention, you're probably not going to escape death at that amount. Right? Radiation is, and it's a strange thing because it's invisible. Right? And so, on the other hand, let's take an example where we take that same 6 sieverts and we spread it out and we continuously dribble it into us over a course of 10 days. All right? What happens over 10 days? Now, I'm not going to say nothing happens to us, but probably about half of us will never notice the effects of that in our entire lifetime. The other half will, there'll be cancers in the future, and a lot of things can happen for sure. It's not safe, but a full half of us would never even notice it happen, right? So if you look at the amount of radiation, the dose rate in space, that's like 1/1000th of the rate of that 10-day example I just gave you. Right? It's a small amount. So somewhere in there, radiation oncology comes in. Most of health physics worries about the very small amount, saying, look, the large amounts can hurt us. So what happens at the smallest amounts that we can possibly detect some detriment? And let's try to get it down to zero. Makes sense. The fewer cancers we can get, the better. But I look back at my dad's records. The amount we gave him to his hip, I now know we could have doubled that dose. We could have divided that dose in two. The effect would have been the same. He would have walked out a week later feeling great. And ultimately, there would have been really no difference. So we sling around these massive amounts of radiation in radiation oncology with no regard for these small, little, trivial amounts that the other side of us, health physics, would have us worry about. And what I want to do with this talk is kind of give you a feel for just the magnitude and the kinds of doses that we are doing in radiation oncology. And then tie it in the end to what would we look like if we were actually going out into space? How does it compare? So the interesting thing about radiation is it's just, and I say just in quotations because it can be painful, it can do some damage, but it's just energetic particles, right? But it has a connotation of something much more devious, radiation. But the fact is, there's photons. You can take any particle and accelerate it, and it becomes radiation by definition, right? And the fact, once you get the radiation to the point where it starts ripping through your body and damaging the DNA, like Dr. Parker was talking about, that's not so great. But smaller amounts will rip through your body at a lesser rate, and your body will repair it. So there's this whole continuum. It's all based on the same idea of energetic particles interacting with the body. And for that reason, we're able to take a look at something as catastrophic as a nuclear plant meltdown, or something as small as background radiation, and we can put them to some degree on the same footing. And that gives us some idea of, more or less what, perhaps a comparison that we could model, and it'll ultimately meet with experiment. But let me give you the unit that you've seen a few times today is the sievert. And that's the unit we generally use, which gives you an idea of tissue damage, more or less. Okay, some particles, they're a little bit heavier, they're bigger particles, they'll do more damage, lighter ones will do less. The sievert. But what does a sievert mean? And so, background radiation, 0.003 sieverts per year. Okay, that roughly speaking, some places get 0.006, some 0.002. Prostate treatment will give somebody like 80 sieverts. All right? Now, you might go, 80, well, I don't know. That's great. Well, how about Hiroshima? The atomic bomb in the center of that blast, what kind of radiation dose was there? 155 sieverts. All right? So, with our radiation treatments right there, with prostate, you can see we're not playing around with the dose, right? It's not a small amount. Now, we're limiting the dose to the prostate, right? The atomic bomb. You're getting it through your whole body. And there's another very big difference, of course, is the timeline in which you're delivering it. Like my original example, 6 sieverts will kill you. Delivered all in a flash. 6 sieverts over 10 days, half of us won't notice a result. So most of what we're doing in radiation oncology is we're taking advantage of the fact that if we deliver this over, 10 days, 5 days, a few weeks, we get massive, massive sparing that allows us to do some really great things and treat cancer. Now, if you look, and here's a depiction of a radiation oncology vault. Right, in the middle there is just the radiation machine. And hopefully most of you haven't had to see this up close, but when you build these things, you have to throw in like 6 feet of concrete, sometimes more. You look, it's a dense concrete, you have to put in lead lining wherever you have any vent, right? $500,000 is an average price just for the vault, which is one reason radiation oncology treatments are expensive, although, well, that's another issue. Well, what do you get for that? You get so that the general public outside of that radiation vault, sitting in the waiting room and so forth, is going to get less radiation per year than our background radiation, 0.001 sievert. Nothing. Nothing. Right? Now, take a look inside. Sometimes we give doses that are up to like 100 sieverts. There's a drastic difference, and that's why we need all that concrete. That's all right. Well, you think about this. Maybe, and stats vary and they change over time, of course, but roughly, you could say maybe 39% of us, one study say we're going to get cancer ultimately in our lifetime, right? 2/3 of us will probably get radiation treatment. So it's interesting because we have this massive difference in feeling about the inside and the outside of that vault. And we'll spend millions of dollars to keep us outside, but 1/4 of us are going to go right inside that vault at some point. And all of those like 0.001 sieverts that we were protecting ourselves from are just going to go out the window. All right? And so, yeah, it's big. I mean, USA, 500,000 people, millions of people worldwide get treatment for radiation every year. So, what happens to the person that goes inside? What kind of doses are these people seeing? Well, you take a look at a brainstem metastasis. Okay, someone with cancer, it's gone into the brainstem, and I've got the crosshairs, and this is actually a patient that I've treated. All right, and I blocked out their name to be HIPAA compliant, and you can see the white dot. That's right in the brainstem. That's not a great thing to have. So we're able to treat in today's radiation oncology with a ton of precision. So that is kind of like a topological map of the dose that we're giving. In this case, we give about 30 gray, 30 sieverts to the center. And you can see by the time we get out to the blue, let's see, I've got another 0.5 sieverts. There's my green line. You can see how the radiation dose spreads out. So even though we've targeted that very small metastases with a ton of precision, kept that 30 sieverts right in there, the rest of the brainstem is going to get, roughly half a sievert. If I go down to 0.1 sievert, you're talking about certainly the 2/3 of the brain. Okay? So that's 0.1 sievert. Remember, we're talking about 0.001 sievert outside the vault. Okay? All right. Now, that's a very small lesion. Expectation is, the benefit of this is this lesion will die. It will not resurface, it will not grow, and this tumor will not kill this patient. So that's worth it. How about something that's not even cancer, though? Trigeminal neuralgia is something we treat a lot of. And this is a condition where there's this little nerve inside the brain that, for some various reasons, it can be little vascular compressions against it. There's various reasons for it. It'll cause excruciating pain to the patients in their face, typically, to the point where, a lot of them are suicidal because of this massive pain that opiates don't control it, nothing touches the pain. So we actually can deliver these massive Hiroshima-type doses to the nerve. Right there is an example, again, a patient that we treated. The maximum dose is about 85 sieverts, right to that nerve, right? Half of Hiroshima, right there. Works about half the time, the pain goes away. But if you take a look at the 1 sievert for that patient, quite a bit of the brain, half a sievert, you're still getting most of the cord, at least half of the brain or more is going to get half a sievert. And this is for something which is strictly a pain syndrome. Nothing to do with cancer. I mean, they'll survive, unless they kill themselves, but they'll survive, right? It's not a condition that's going to spread. Well, consider good. Another one, which also is it's a condition almost like a cancer, but it's not going to spread. And a lot of times, it'll take years and years and years, a meningioma, before it grows and puts pressure. An example of some lines, there's the 10 sievert line in the brain. Right there is the 1 sievert, so the entire brain is going to get roughly 1 sievert. Okay, so you're getting the idea. Now, you might say, okay, this is just a piece of the brain, though, so maybe not so bad. If what about? Here's a treatment that we do a lot of: whole brain radiation, and it sounds as awful as it actually is. It is and we've been doing it for decades, where the idea is people may, sometimes they may have some brain metastases, several of them that we want to treat, and we can't just go cherry pick them all. In the past, we didn't have the machines to cherry pick these ones. It may be cases where we think they're likely to get metastases in the brain. So prophylactically, we give them whole brain radiation. And I'll give you a screenshot of a whole brain patient that we have actually done. And I don't really have to say much about it. So that was 37 sieverts to the entire brain, all right? And if you look at the 10 sievert, that goes down right into the spinal cord. In some cases, we bring that dose down specifically and treat the spinal cord. It's not in one shot. It usually happens in 10 or 15 days. All right? So, what about the rest of the body? Here's a lung tumor. It's close to the heart. Big thing is this 10 sievert is covering pretty well from top of your stomach to your back in the region of where this is. 10 sievert. No, I'm sorry, I wrote that wrong, but that's 1 sievert. Okay, so that's a 1 sievert dose right there. That's the entire field that you're getting. So in the center, we treated this patient with 40 sievert. All around their entire thoracic cavity is a sievert. All right, 1 sievert. Pelvic, I mentioned prostate, we treat to like 80 sievert. Here's something where we treated pelvic nodes. The orange is hotter. We're still talking, there's a 5 sievert is all the blue. Okay, so bottom line is, we're shooting these people with an awful lot of sieverts. And then the question, probably for laymen certainly, and probably should be for any of us treating people, are we just killing people, right? Good God, is this even reasonable? So there's this fantastic study where National Cancer Institute looked at registries over the last maybe 30 years of cancer patients and followed like 2 million of them, and said, okay, what's the chance of people that this is radiation and chemotherapy and every kind of treatment, but what is the chance of somebody getting another cancer from the treatment? Okay? All treatments combined. And it came out to like 6% chance. So normally all of us have a 39% chance we're going to get cancer. This goes up to 45. That's covering all of these treatments, including whole brain, including everything. And there's a huge amount of variation within it, according to where you're getting it and all of this. But as a kind of rough feel for it, a few percent, which I thought it was kind of surprising, right? And they didn't just look at what happens over 5 or 10 years. They're looking at 25 years. So this is a very long-term study. Bottom line was, it's not like everybody is getting secondary cancers from the radiation treatment. They're not. Certainly, the closer you get to where you're beaming the dose, the more chance of cancer in that area. And that's true. And in fact, all of the modeling that we heard about with Dr. Parker. I mean, this is great stuff and true stuff. At some point, I think we'll get to a position where we'll be able to do really, really good modeling at this low level and get up to, but at the moment, we've got huge amounts of uncertainties at the low levels. And so in radiation oncology, we just, don't worry about it. Yeah, an argument could be, well, all right, but all of these treatments are still part of the body, right? You go out and galactic cosmic radiation is your entire body. So that's a different story. That's an argument. But that's not all. I'm going to show you something that's I find it a very disturbing image. Total body irradiation. Something we've given to tens of thousands, maybe 100,000 of people that are generally in a situation where they're going to get a bone marrow transplant. And they have something like leukemia. And so we need to give them enough radiation to knock everything out prior to this transplant. Okay? And the technique for doing it is that you have the radiation machine and you take a patient and you put them across the room. I mean, it's this goofy, right? We have the machine where normally patients right inside the machine. Instead, we put them at the end of the wall. And we turn the machine sideways and we point it at them so they can hit their entire body. This is a technique that is not like 5 years old, right? This is like 20, 30 years old. Here's an actual example of a patient in a little holding tank waiting for their radiation, their whole body radiation, total body. It's absolutely amazing that we can do this. Here's the dose we give, 12 sieverts. 12 sieverts. In how long? 3 days. We break it up, 2 treatments each day. Boom, 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 right? There's the red where you see 12 sieverts over this entire patient. All right? So, all right, what happens to these patients, generally speaking? And I'm going to say, oh, they're fine. They never have any side effects. They do have side effects. 5 to 10% additional cancers over 10 years seems to be a common number. This is certainly more than with the other radiation treatments. We're talking about maybe 39% going to now 49% chance you'll get a secondary cancer. But still, this is still considered to be a curative treatment. So, I look at the trip of Mars. We've seen here, beautiful measurement was actually made on the Curiosity rover going to Mars, so it's not just a theoretical thing, right? Comes out to like 0.6 sieverts, right? Just from the trial, 0.6 sieverts, right? So I look at this, I go, okay, so 12 sieverts in 3 days for this 10-year-old kid, and 0.6 sieverts in a year for our astronaut, right? So why are we worried about that? 0.6 sieverts. Why don't we? Space agencies looks like they have a 1 sievert limit. NASA is kind of clever. They've got this 3% from an effect of radiations-induced death. All right, so it's interesting because you can model it in any way and come up with lots of numbers that come out to a sievert. But with some current, conservative estimates, it's like maybe 0.3 to 0.4 sieverts would be the NASA estimate. If you look at the lower limit of that. All right, so somewhere 0.5, 1 sievert is what the people are doing. And from that article, in fact, there's, they even state, well, this could be, and I copied verbatim from it, this could be problematic. Because until we get a safety factor narrowed more, we may not be able to go to Mars, is kind of the idea, right? Because what if it's like 1.6, not 0.6 sieverts? So I would say, for something where you have a bunch of people headed to Mars, we should certainly be giving the same kind of latitude in terms of radiation dose that we would give to the millions of cancer patients, a quarter of them are going to be us eventually, right? And I think most people would gladly accept that additional risk. If it's 5%, if it's 10% additional risk of a cancer, I'd say, look, 10 sievert is where, yeah, now it's starting to get like huge. That's radiation oncology level. Right? You start to worry, not 1 sievert. I'd say go back and forth to Mars 10 times before you start to worry about it. And then the final thing is this idea of, well, it's 3% chance of death, right? Okay, so half of the people, probably less now, will actually die of a cancer. Our treatments are getting better. But I don't think it's a stretch to say 10 years, that might be like 1 in 50. The kinds of treatments we're seeing with targeted therapy, immunotherapy, et cetera, are blindingly successful and fast. If you were to say our risk of death from a cancer might be 1 in 50 down the line, well, that 3% NASA limit now actually comes out to about 10 sieverts. You know, you multiply it, and you say, well, okay, that was so. You know, ultimately, well, that's terrible for my conclusion, but you get the point. And I think ultimately we should look at radiation treatment or doses going on a trip to Mars as being, you say, well, the radiation, that's what it is. It shouldn't be a prescription of how much we can limit, but maybe a question that we get the answers and we observe it and we study it. But the levels are so small compared to radiation oncology that I think they're not even worth being worried about. So that's it. Thank you very much.
Well, wouldn't you say that it's Mercedes that's telling the medical radiation people that it's okay to radiate people? In other words, they're paying. Because you didn't understand them.
Oh no, I absolutely do. The thing is that so radiation happens to be a curative thing. So people with lung cancer, for example, a primary lung cancer, 20 years ago, you would have to get your lung removed to cure that cancer, right? Right now, if we get a primary cancer, we're able to treat it and get same surgical results, if it starts out small enough with some of our precision treatments. So I'd say radiation does a fantastic job of curing, and the intent is usually curative and certainly palliative. So yeah, the Mercedes argument, I think it's paid way too much, and I think it is a bit of a scam in that way, right? The way we get the money for it, but that's a political issue more than anything. Radiation does work.
Yeah, I would interpret the result of what I heard that we overestimate the influence of radiation for Mars mission, I don't know, by a factor of 10 or 100. I mean, those who say you will get cancer when you go to Mars, is that this order of magnitude? Do you think personally it is overemphasized?
Yeah, I think ultimately most estimates will be you might add a couple of % chance that you're going to end up with a cancer that kills you. Maybe a 5% chance that you'll get it.
This is a 3% that Robert Zubrin is always stating.
Yeah. Yeah, I think 3%, 5%. It won't be 10%. Mm-hmm. Yeah, and it very well may be less than that because the dose trickles in. Yeah.
Thank you.
You mentioned that it's important about the amount of the dose and over the time of period that you get it.
Yeah.
There's also a different type of radiation, whether it's high energy ions or whether it's,
correct.
Could you speak a little bit about how space radiation differs from the type you use in oncology?
Yeah. So most of the space radiation, galactic cosmic radiation, is going to be protons and helium atoms. Okay. There's going to be a 1% that's going to be bigger atoms, right? We actually do treat with carbon atoms. There's treatment centers that use carbon atoms to treat. There's treatment centers that use neutrons to treat. We don't know precisely about very high, very, very high Z particles, that 1%, how exactly they're going to affect. The idea is they'll probably, if they're high energy and they directly hit you, they'll probably cause a greater effect in the body. That's generally the idea. But we've been treating with protons now a lot, right, which is going to be a lot of it. Results are actually experimentally very good. So in theory, the higher you get, you can do that 1%, and that's part of this modeling. I think that's going to pan out, really give us some more precise answers. But it's an uncertainty. Yeah.
Yeah, Brian, very appreciate your approach here and putting things in perspective is what you're doing. And but still, is there a means of teasing out who gets the cancer and who doesn't? Do we understand enough yet? That's kind of what I was talking about earlier about and I raised the issue. I didn't have a solution. Is to determine who is more susceptible than others to a given radiation dose.
Yeah, I mean, rule of thumb, and I'm not a modeler in radiation oncology, but rule of thumb is we generally think, probably about a third of the cancers, we have no idea why people get them. A third of them are directly related to stupid things you do, right? Like drink and smoke and whatever and work in a radium mine, right? And then the other third is probably going to be things like nutrition, right? And these other things are much more subtle, your diet and how you're breathing, these background radiation, that kind of thing.
Slow protons.
Yeah, maybe. So, sorry.
So we're actually out of time. We're out of time. Brian, find out after this in the room, so if you want to stick around and ask questions, you're welcome to do so. Thank you.
Thank you.